So today I'm going to talk about robot learning from human experience and how scale is starting to change what robots can learn and how they learn. I'll frame the talk around three hypotheses. So first, robot capabilities can scale with human data. And second, human data will soon be abundant, to be sufficient enough to the point where we don't know how to do about it. And third, progress requires scaling both the science and the data. So they are the hypotheses, not facts, but I hope this talk will provide some evidence, concrete evidence that they are becoming true. I hope I don't have to convince you that robot learning have made a lot of progress. And one of the key factors is that we have rediscovered teleoperation to be a really good way to teach a robot how to do really complex tasks like making laundries, clean bathrooms, or doing warehouse tasks. And they're really being deployed in the real world today in factories, in laundromats. And I mean, they're starting to be usable, but they're not mature yet, but we're seeing them in the real world today. So before diving into the technical talk, I want to step back and ask a more fundamental question. Why do we believe this whole data-driven robotics direction will work at scale? After all of these hundreds of billions of dollars investments in robotics right now, this underlying belief that we all think is going to work, right? So the answer really is largely based on analogy with the type of AI we're using today. At this point, a large part of human knowledge is being captured by the internet. They get downloaded, cleaned, and absorbed by these large foundational models. And in other words, modern AI succeeds because we found a scalable way to transfer our knowledge to these models through the internet. We, the robotics researchers, are essentially trying to apply the same idea to the physical world. Instead of semantic knowledge, robots need sensory motor knowledge or physical intelligence. So teleoperation really provides a mechanism to transfer this knowledge. By controlling robots while recording what a robot sees and what actions should be taken, we are building a direct mapping between the perception action or the input and output supervision for the robot's body. In a sense, teleoperation allows to transfer human physical intelligence to the robots. But despite the simplicity of this analogy, in reality, teleoperation creates a very, very tight knowledge transfer bottleneck. And I argue there are two major factors to this bottleneck. The first one should be familiar to some. It's the scalability problem. If you have ever tried teleoperation, you know it's very, very unintuitive. It takes a lot of practice to get it right. More importantly, teleoperation only scales linearly. The amount of data we can collect grows only with the number of robots multiply the number of human teleoperation hours. And compared to the internet scale data used to train modern AI systems, this is extremely expensive. The second challenge is more subtle, which is the fidelity of the data. Humans have enormous sensory motor knowledge about the world, but teleoperation captures this knowledge only when a human deliberately acts through a robot, using interface like VR devices. And this creates a very indirect feedback loop that meddles with our natural behavior. As many forms of intelligence are difficult to deliberately demonstrate through teleoperation, think about subtle behaviors like kneading a dough or picking up a card by sliding to the edge of the table and picking it up, or when your hands are full, so you open a door instead of using a hand to open a door, right? So all of these motions, we don't think much. We do it as we go about our daily lives. And demonstration, when we teleoperate, we inevitably simplify these behaviors to the point where the control is much, much easier for the robots to carry out. So in other words, teleoperation is not just a narrow pipe. It is also a very, very lossy one, loses a lot of our human knowledge, and wastes all of these intelligence. So the question we want to answer is, how do we transfer sensory motor intelligence to robot at scale and without losing the fidelity? And our proposal that we've been doing in our lab is to break this bottleneck by going directly to the source. We want to capture the human experience directly with no robots involved. And we want to make sure the data contains all the necessary information, including sensing action data to supervise the robot learning model. And such data should not be collected as demonstrations, but captured while humans are performing natural behaviors in the real world. And this talk will be 3 parts. I'll describe some of the work from our lab. I call it science human-robot transfer, but it's really just the style of research we've been carrying out. There are many different ways to do human-to-robot transfer. And we want to examine that if we scale up this approach, what happens, right? What happens when we have a lot of human data? And finally, I want to also talk about the problem that because this is an extremely resource-intensive research topic, can we also scale the science to allow the community to drive the collective progress of this topic? With that, this brings us to our first research milestone, which is called EgoMimic, Scaling Imitation Learning via Egocentric Videos. Some of you might have already seen it. The core of this research topic is really to capture embodied human data from an egocentric view at an eye level. So we want to capture our authentic experience through visual sensing. Unlike third-person views, egocentric data capture how we naturally perceive the world at an eye level. And specifically, we use Project RA glasses to capture this data, which essentially capture a lot of multimodal information, including where the heads are, where the hands are. I will talk a bit about why this is good, but things to take away is that these are just glasses, so they don't meddle with our behavior. It only captures it. And our work, this specifically, is about turning these raw data streams into what we call embodied human experience that can be treated as equals with robot data. So our key hypothesis is that humans are just kind of weird type of robot. If you can measure it, if you can put sensor around it, you can treat that as the human data as robot data and want to be able to use that data directly by bridging sensing, action, and kinematic gaps. And we want also to develop a scalable way to learn from these data. So we want a policy learning method that scales with human data. Let's first talk about how to align embodiment and viewpoint, which is kinematic and visual gap between human and robots. For embodiments, so we really believe that in order to better learn from human data, the robots should be more human-like. So you might think the first reaction is, yes, humanoids. But back then, when we started this project in early 2023, there weren't that many humanoids around. So what we had to do is to build a robot of our own. But it really kind of embodies a lot of our design choices that carried through later in our other works. So it has to be kinematically similar to humans. I mean, 6-off arms is pushing it, but we tried our best. And another design choice we made is actually we want the hand-eye configuration of the robot to be very similar to the human so that we can bridge any sort of these visual gaps and also hand-eye configuration gaps between human and robots. And what we did was directly mount the glasses that we use to capture human data directly on the robot so that we can mitigate any of the sensor hardware gaps between human and robot data. Another interesting problems that we have to solve is the hand-eye motion. So if you look at this egocentric view data, you know that humans move a lot. They move their heads when they look, and they have information-seeking actions. They move their body a lot. But our robots are kind of stable base. It has a torso but doesn't move, has a head but doesn't move, right? So it has the stable coordinate system between action relative to the camera. But this is how we created this kind of action supervision for the robot, right? Because the reference frame is the same, so it has the trajectory that we can parse. But humans, they move a lot. So the question is, how do we actually parse this and convert the data to like a robot, like human data to something that we can train robot policy with? So we really need to stabilize the reference frame for the actions. And luckily, Meta ARIA glass gave us really, really robust visual inertial odometry, or SLAM. They've done it through SLAM. So what we did, put simply, is to transfer the future hand poses into the current observational frame, and that allows us to kind of get these kind of a consistent trajectories for action supervision to create like visuals like these. So this visual is only possible because we have very, very stable, a good quality visual inertial odometry for the camera. And once we align this kinematic and visual gap, we play also a lot of other tricks. So initially, we kind of just did the simplest thing to make human-robot look alike. For example, we put masks on the human data to make them look robotic, and all that kind of things. But the learning architecture is quite simple. It's just a gigantic transformers where we randomly sample batches of human-robot data, and we line their input-output space, and we train this model together. And the hope really is that this architecture can come up with a representation space that aligns human and robot such that the performance of the robot policy can scale with human data. That's our hypothesis. I'm going to show you this is not exactly the case why this policy performed well in the next work. So we tried this on a variety of tasks, including like this kind of grocery bagging tasks. So like just show that it works in closed loop fast enough so you can see these reactive behaviors. Of course, we made it full shirts, these tiny toddler shirts. And we also made robots make coffees for the students. And I mean, it doesn't succeed all the time, but you get the idea. I mean, we really want to show that human data does drive up the performance of robot policies. I'll let her actually drink the coffee and move forward. So quantitatively, what we saw was that our hypothesis is that human data will scale robot performance with human data. So this plot x-axis is the hours of data we spend on data collection, and this blue curve is when you only collect robot data through teleoperation, and y-axis is the normalized score of the task. So you can see that as we collect more teleoperated data, you see a mild scaling curve that performance gets better as expected. But when you add 1 hour of human data to this at a 2-hour mark, so when we combine 2 hours of robot data with 1 hour of human data, you see a dramatic performance jump. And this reason is that we do tasks a lot faster than robots. Human hands move a lot faster than robot hands. So sometimes we can demonstrate tasks up to 10 times as fast as robots. These are like very experienced teleoperators, right? My students are really good at teleoperating robots. And even that, humans are a lot faster in their naturalistic speed. So we also kind of wheeled robots to different parts of the campus, Georgia Tech campus, to show that the policy is robust and all that kind of thing. There's nothing really new here. It's just that we wanted to really show that this policy works, right? And so right hand, lower right, the students basically keep tossing new chip backs to it just to try to see if it fails, right? So after this project, we asked ourselves, is this end of the game? Like, is this it, right? Like, what have we solved the problem? So what we learned is that really scaling we can scale robot performance with human data. That we have verified repeatedly later in our work. So the same recipe works. But what we are not happy with is that, if you remember, we had to collect both human and robot data. And in fact, we actually had to collect on the exact same task in the same setting. And this really kind of defeats the purpose of having human data, right? Like we don't want humans to be like also collecting data and have robot data, teleoperation data. So what we really want is to have robot perform the tasks that only exist in human data. We want to enable this kind of zero-shot transfer from human to robots. So what is the ideal picture here? What is our mental picture of why this might happen? So our ideal picture, this is just one specific scientific hypothesis we have, right? There are many other ways to look at this problem, is that we want to learn a generalizable embodiment or domain invariant policy latent space, where let's say we have data from both human and robot for folding shirts, right? Like the blue and reds are robot and human data. And through some magical encoder, we bring them to latent space. And we have a shared decoder, which is a policy that decodes action that can kind of control the robot to do the same task. And the nice thing is that if we can do this, then maybe we can imagine that giving a new task, like folding shirts, folding shorts, we could also project this into space. And without robot data, we can also use the same policy to decode it to action to make the robot do things that's only shown in human data, right? So this is really our ideal picture of what should happen. So does simply co-train these two sources make that happen? The answer is not quite. So this is my student Ryan, who really kind of dug into the latent space of the policies after co-training these two models to do these two sources. We discovered that they actually don't align that well. You can perfectly distinguish these two sources despite you mix them in a training set. So the hypothesis that, like, basically, we just made a hypothesis, right? Like, if we can align these two spaces better, maybe we can enable better transfer. So this is where the second follow-up work of EgoMimic come from. So it's called EgoVerse. So we really did the simplest thing, right? We tried to align the two distribution space through a somewhat distribution alignment objective. In this case, we use our joint optimal transport. We basically simultaneously align both the observation, so latent space and the action space to the same space. And the nice thing about optimal transport, for those of you who don't know that, is that they actually preserve the respective marginal distribution of both domains, so that you don't actually have to deform one distribution to match the other. So you don't actually destroy the performance, what would have been the performance of the robot-only policy just to align these two spaces, right? So that's the nice thing about joint optimal transport. And the actual transport is just a differentiable loss function that will put in the network when we train the behavior cloning loss. The transport map is when you compute per batch. So you try to see which pairs should be mapped together. And the cost function is something you define by yourself. So these are basically human policy latent and action and robot policy action latent. So you design some latent cost functions in this space so that you think these should be aligned in a sort of not a constrained sense, but more encouraged sense. So we actually tried a few different cost functions, and we realized that just matching their dynamic time warping distance in spaces actually just works well. But you can extend this cost function to other things like language description, right? If the two data points have the same language description, maybe you should map them together. So after training this model, and we compared the latent space, and we discovered that indeed they start to align. So on the left-hand side, you can see that the orange and blue dots are a lot closer, and you can see that there are a lot more blue dots because the blue dot, they're still part of the space that the humans will not do, right? So, but you can see that, the blue dots are kind of behind the red dots, but they have a high degree of alignments, especially in this part of the space, right? And if you actually look at the nearest neighbor points in this latent space, you see that they are very behavior similar in similar stages of task. So you can see that for this task, it's just kind of pouring the beans out to the cup. And quantitatively, we show that this indeed works well. It further improves the co-training performance. This is still the same setup as EgoMimic, so we have the same tasks, same demonstration, same task, and just does it further drives the performance for co-training setting. But what we are truly curious about is, does it enable this sort of direct transfer from human to robot, like a new thing that human does that robot doesn't do? And we decided on a task that is slightly contrived, but really kind of shows the spirit of zero-shot transfer. Is that we have this like a small cabinet, like a box of drawers, and then we demonstrate a task on the blue region from both human and robots, and a purple region of both human and robot, and a red region is only demonstrated by the human. So our hypothesis is that if the robot can perform tasks in this red region, that means that it must have transferred something from the human data only, right? Because we never showed this tail operation in that region. And indeed, this is what robots was able to do, not perfectly. It has a performance drop in this region. And quantitatively, we saw that, but despite that, we actually, EgoBridge was able to get non-zero performance compared to any other baseline. So all of the other pure BC baselines without this kind of realization failed. So we were more confident that this representation alignment hypothesis is true. But we only verified that at small scale. So I'm going to talk about what happens at scale later in the talk. Okay. So then this is sort of the representation alignment story. We went on to study other parts of the human-to-robot transfer. For example, we felt that mobile manipulation is a perfect place to study this problem because teleoperating robots for a mobile sense, for a mobile task is really, really hard. We actually built this a version of this Aloha station in a lab. When we tried to teleoperate it, it was very, very difficult. So it is tedious and expensive, costly to collect. But human data, on the other hand, we move around all the time. We don't think about when we are doing tabletop versus mobile manipulation or just navigation. We just do things. And with these devices like Project Aria, we really do have information that informs us about like how human does things in the world, right? For example, we can get the SLAM map, we can get where the heads are, where the hands are in the spatial sense. This is just from one task demonstration, right? All of the information you see on the screen is just from that demonstration. We didn't do any like multi-traversal to construct this map or anything. So we really have the technology to capture mobile manipulation information from human data. So with that hypothesis, my student Lawrence kind of just basically applied the same recipe to mobile manipulation, right? So it's called egocentric mobile manipulation, or EMMA. And I'm not going to get too much details because I have a lot to cover. Really the recipe is that we want to build an architecture that can learn mobile manipulation, including waypoints, past waypoints, and everything, just so that it can learn the policy. And the system-wise, we had to do basically manual retargeting to a differential drive because differential drive, as you know, they can only move. You only have like a rotational and a linear speed, but humans move holonomically, right? So we actually had to do some retargeting to make it work well on the navigation part of the task. And what we showed is that it's actually exciting that we can show for most of the tasks that are majority just navigation with a little bit of manipulation, you can do a zero-shot transfer. You don't need robot data for navigation. Navigation just transfers zero-shot to robots. And with the manipulation-heavy tasks, we had to do a bit of code training, but there's the performance gain is a lot, right? So from human data. And I just want to show some of the more challenging tasks we've done for this task, which is kind of grocery shopping. We're no longer just bagging groceries. We're just kind of putting stuff in the baskets and moving to different parts of the workspace to hand over to people. Right. So this is code training. So this manipulation part of this is code training. There's no mobile human. There's no mobile teleoperations. Just static teleoperation data plus mobile human data. And when you compare with just pure behavioral cloning policy, you see that behavioral cloning policy is very, very fragile when you have long horizon tasks. What we discovered is actually most of the failure comes from navigation stage. So if you actually have more data on the navigation stage, they're less likely to drift out of distribution, and they're more likely to succeed for long horizon tasks. So this is where the benefit of human data comes in. And we also showed that for a majority navigation task, we can scale the performance just by giving them more human data. So this is one of the handover tasks where you have to travel to a different part of the room and hand over a wine glass to a person standing at the kind of random part of the room. And we saw that this kind of very nice scaling curve, and we were pretty sure this is true because the student actually did 50 evals per data point, which took a very, very long time. But we're fairly sure that this scaling curve is correct. Okay, so and after that we are very excited and we started working on a lot more direct transfer. For example, we started bringing up a more human-like robot. So this is one of the rainbow robots where we started doing direct retargeting to a full humanoid with wheel base. This is just a replay of the human data. It's not teleoperation, right? It's just human does it once, retargeted to robots, and the magic is actually is on the kinematic retargeting side of things. So we actually put a lot of effort in retarget the full human post into robots through an analytical solver. So it's really fast, can run at 2,000 hertz, and we'll also be able to retarget it to a mobile manipulation task like closing fridge door. So this is ongoing work. So we're still trying to improve the system. The controller is still not great yet. Okay, but we're very excited to bring this to more human-like robots. So the second part of my talk is about what happens if you scale human data further, right? We've shown this in like on the order of like 3 hours, 5 hours, 10 hours human data, and we saw that something great happens, but we don't know what happens at scale. And I kept telling that human data scales, but does human data truly scale, right? So I actually gave a talk on a very similar topic about a year and a half ago, so November 2024. This is one of the last slides on my talk. I preached that embodied human data is robot data in disguise, and robots are become more human-like and whatnot, right? But one thing that I basically said is that the data capturing technology is ready, is advancing. And what I was referring to is that people will start buying these kind of devices from companies like Meta and Google. They'll start wearing these AR wearables, start capturing data. Maybe in 5 years, we'll have enough data to train these kind of foundation model from human. But what happened later was something that we did not expect. You might have seen this news, maybe. Why hundreds of people in LA wear cameras while doing their chores? This came out two weeks ago. And there was another CNN news teach you how to make money just by wearing your iPhone in your head and get money from it, right? So what happened was that our research, I think contributed to this broader capital interest in paying people to get data to train robots. So in other words, some of our research caused the data to be more abundant than what we had expected. And that expedited the progress of research to the point where you could actually download this app today. It's called Task-Out app. It's from DoorDash. And wear a camera on your head, and you can start collecting data and sell the data back to DoorDash. And DoorDash will sell it to one of the robotics labs and to train foundation models for robotics. Okay, and there are probably about more than 100 companies started in the past 8 months or so, or 6 months or so. Their main goal is to do labor arbitrage. They pay people with wage and collect data and wear cameras or devices to collect data for them, right? So, all of that is like slightly dystopian and all that, but now we can actually answer the question: what happens at scale for these reasons, right? So, in collaboration with NVIDIA and Physical Intelligence, we verify these in kind of 2 different stories. One is called EgoScale, where we basically, you can think of this as scaling EgoMimic 10,000 times bigger and see what happens. And the other is a more subtle view about human-robot transfer is how do we enable human-robot transfer emerge without supervising it through aligned data. So it's sort of an emergent behavior of human-robot transfer through multi-embodiment learning. So EgoScale, the first hypothesis we had is that we just need to scale up human data. So we went in and actually just bought a lot of data. And NVIDIA basically, we bought a lot of data. So 20,000 hours of data, very similar, like it's the exact same format as what we used in EgoMimic. And the second hypothesis is that if we make robots more human-like, the transfer will be a lot easier. So if you recall, our 2023 robots like this, right? 6 off arms with grippers. And because I guess we wanted to verify the hypothesis, we had resource, we had two 7-off arms with 22 degrees from dexterous hands. These are the state-of-art robots this is sort of the best system we can have. So the upper body is very, very human-like. And EgoScale is just a recipe to see how we can leverage these sources data. And it's a very simple recipe where we kind of if you know about language model, you know there's a pre-training stage, there's like post-training stage or fine-tuning stage. So it's very similar. So we have model pre-trained on 20K hours of human data. we have a mid-training stage that's very similar to what we did in EgoMimic, which is that we have aligned human and robot data on a variety of tasks to form a foundation for the transfer. So you can think of that as teaching this model that this task, when done by humans, looks like this. When done by robot, looks like that. Right? So we have about 300 or so of these mid-training alignment data to anchor the transfer. And then we showed that it can indeed transfer through, let's say, one shot, or we actually tried 0 shot. It didn't work quite well, but we really tried to verify that. Can we train robots with just human data, trained to do things that only show in human data, right? And one of the sort of the obvious to me conclusion was that scaling still happens. So we had plotted this. We didn't expect this to happen like this perfect, but we really did just plot a training curve of x-axis being the number of human hours, data hours for pre-training. This is from 1K to 20K, and there's a log scale. And y-axis is not performance. It is the action prediction error on the validation side. So not success rate. Just make sure it is not success rate. But what we saw is a log linear scale, right? So we really have a further scaling when you have more data. Well, we didn't change the model too much. It's the 3 billion parameter model, but it is able to fit all of this data and keep scaling. And it also happened to be that the pre-training model when training on more hours data, when you post-train on a specific task, it performs better. So I wouldn't call this a scaling law because now, I mean, it's just we speculate that validation error correlates with performance. I mean, if you have worked on calibration behavior cloning before, you know that at small scale, this is almost never true. Validation error do not correlate with success rate. But at scale, we discovered that this is actually a pretty reliable predictor of success rate. So the better you are at predicting human behaviors you have never seen, the better this model will be at transferring to downstream robot tasks. Again, this is just empirical observation. I'm not making any suggestions that this is the truth, right? So we kind of post-train this on a variety of tasks. One of the more kind of fancy tasks is actually assembling a toy car. So uses tools and has to have aligned this pretty accurately to be able to assemble this car. And we also trying many other tasks right now that looks more realistic, like more economically interesting than just assembling cars, and it also works. And we also have tasks like using syringe, and it just tests the precision of the manipulation, and things like manipulating thin shell objects like cards. And we also very interesting answer the questions that we started a year or two ago, which is, does scale enable better human to robot transfer through mid-training, right? So what we did was, again, the mid-training stage is about collecting a lot of diverse human-robot aligned data and see if this enabled transferring tasks that only showing human data to robot policy, okay? And what we did is that once this model is mid-trained, we provided one robot demonstration of a new task never seen before, and 100 or so human demonstrations to the robot, to the policy, and see if the robot can do that task. So it's not 0 shot yet. We're trying, but 1 shot, pretty reliable. So for example, this is one of the mid-training tasks, like rolling shirts. And if we have one demonstration of folding shirts plus 100 demonstrations of human folding shirts, it's able to reliably fold the shirts. So what we have achieved is a 1-shot transfer, not 0 shot, but it's getting there. We actually tried this on 0 shot. It does something reasonable just from human data, but it's not quite able to achieve like more than 10% of the success rate. So still trying this. But there's a sign of life here. Very exciting. And also try this on like screwing different bottle caps and everything. And quantitatively show that there's a stark difference. So the yellow is mid-training only. So there's no pre-training. just mid-training only, right? So we mid-train this, and then with one shot plus human data, we see that there's moderate performance, not zero for the less challenging tasks. But then with the mid-training plus pre-training, we were able to achieve very good performance. This is the red bar, right? So the way to interpret this is that the alignment, the mid-training is a bridge between the pre-training and the robot policy. So this is how we bring the vast prior from like 20,000 hours human data to the robot performance, is by teaching the robot, this is how the human looks like when you do this task, and this is what a robot looks like when they do the same task, okay? And also tried to deploy this on a different robot. This is a G1 robot. We didn't do much tuning. This was actually done like 2 days before deadline. And it just same recipe works pretty well. So we saw decent performance improvement on a variety of tasks. So we're fairly confident that this recipe works beyond just like 22 degree freedom hands plus like very capable upper body. So it should generalize reasonably well to other embodiment as well, okay? So then we have another question, which is that, is scaling human data all you need to enable transfer? What we learned from EgoScale is that supersizing human data improves robot performance at scale, right? So scaling plus alignment was a recipe. But we do need aligned data for like a variety of tasks to form this support to enable the transfer, right? So this is what we need. Like for a new embodiment, we had to collect some mid-training data to enable task level transfer, and this is kind of tedious. So we started asking us, why is that? Why is it so hard to adapt to a new embodiment? So what we kind of hypothesize is that, in effect, we're really just manually constructing these alignment sets to teach the robot. It's almost like supervising the transfer from one robot, from human to one robots, right? By constructing these sets. And a different perspective is that maybe human to robot transfer is simply one instance of a broader cross-embodiment learning problem. Maybe if we can train the model with more embodiments, like more different kinds of agents that do things in the real world, maybe this human to robot transfer is no longer hard, right? We can form a generalizable transfer from human data to any robots. So luckily, we do have that data. We have, over the years, the robotics community have collected a lot of data from different kinds of robots. And one of the data sets called OpenX embodiment, some of you might have heard of it. It's just like all sorts of different robots doing things. With that hypothesis, I'm going to briefly talk about our collaboration with Pi, which is led by my students, Simmer, that we verified the hypothesis of human to robot transfer can be an emergent property of if you train on more diverse embodiments. And the most important figure is this. The x-axis is the diversity of pre-training set, and the y-axis is the task performance. So if you scale the diversity of robot pre-training data without having any human data, you have a moderate scaling curve. But then, if you add the human data to this different points on the pre-training set by post-training this model, you can see that there's a bigger and bigger jump in performance, which means that maybe, right? This is still just empirical observation that maybe when you train on more embodied pre-train your model, this is a vision language action model, VLAs. When you pre-train this model on more diverse data, it is easier to transfer human data to downstream embodiments. And we also verify this in a similar sort of testing plots that we show that when you train on more diverse data, the distance between human and robot data in the latent space become much closer and closer as you kind of scale the diversity of the data. So this further kind of corroborates our hypothesis that this may be an emergent property of diverse training. So the way to think about this is that if you force your model to like cross and like learn a lot of different embodiment, maybe it will just like abstract everything into a embodiment agnostic latent space. Okay, and I mean these are some nice videos that they made. I'm going to just show you something here. The key idea is still the thing that I just told you. This is just one thing that showed it's the robot became capable just by learning from human demonstrations. And one thing I want to mention is that this perspective is also saying that we need a robot. The more subtle view of this is that we need a lot of these primitive actions to present in the pre-training VLAs, because if you can imagine that a lot of these diverse pre-training robot data is giving the policy the ability to actually do these kind of little primitives, like picking up nails and putting nails in the toolbox and everything. What a human data essentially does is to string these behaviors together to solve a long-run task. So we don't actually need a lot of human data to make these work. So this kind of brings to actually two perspective of human to robot transfer that happens only at scale. The first perspective is more straightforward, is that if you have a lot of human data, if you post-train a robot data with some aligned data, aligned human data, robot data, and human-like robots really enable strong human-to-robot transfer at scale, right? This is just pre-training, post-training story. But what the Pi collaboration is saying is that maybe the foundation is not human data, is a lot of diverse embodiments that supports the transfer from more diverse human behavior to different robots, right? So it's really diverse embodiment data allows human robot transfer to emerge. And I'm not suggesting if either of this will be the final picture. I'm just saying that at scale, different things would emerge that don't happen when you work on small scale problems, and depending on what hypothesis you have for how you view human robot transfer problem, you might find different things. So there's not a single answer to this human robot transfer problem, and it's a vast space of exploration to be done in this space. Okay. So on that note, I think it's time to answer the question that if a lot of things happen at scale, if academia, what's a robot academia, right? How can we actually drive the science of this? Is it just a big company or the fancy frontier lab problem now, right? So the final question I want to kind of hint at is maybe there's a way for us to also scale the scientific understanding of human-to-robot transfer. Because making scientific progress is not really a company thing. It's a collective community thing. If we look at the history of AI, right, many of the major breakthroughs were enabled by community scale infrastructure like ImageNet, MS Coco enabled the blossom of a lot of the deep learning techniques and computer vision advancements and detection, segmentation, and all those kind of things. And Common Crawl, Atari games enabled advances in reinforcement learning for a while. And Superglue really stress tested a lot of these language models. And Common Crawl was part of the foundation for a lot of these modern LLMs because it's just basically internet.zip, right? And the nice thing about human-to-robot transfer, despite the fact that it's very costly to collect data and you still have to evaluate on robot, is that we can finally agree on a source data, right? If you have been in robotics for a while, the major problem is that everybody has different robot. We all study different robots. And despite the fact we're still having different robots, if we are studying the human-to-robot transfer problem, the human part, we can all agree on. So we have it's likely that we can have a common foundation for studying this problem. And we have more consistent embodiment of robots, and that allows us to kind of maybe to get together data to study this problem. And but we still need a lot of data, right? We still need a lot of data to study this problem. And I kind of did an estimate of what are the usable data, open source data on the internet for human data these days. It's roughly around 10K. So I know there's a lot of startups kind of branding themselves as oh, I'm released a new data set. If you look into them, is that actually usable, super usable? So I did an estimate. It's roughly around 10K hours of usable data. But I theorized that maybe we need maybe 1 million to 10 million hours of human data to be able to see more emergent behavior scale. So it requires a community effort to actually drive up the data set size and their understanding the whole ecosystem around this to make progress, at least not that exists outside of these frontier labs. So this is why we decided to do a project called EgoVerse. This project was actually started about a year, about like late 2024. So it took more than a year to complete. It was a lot of effort to actually put together a few labs and companies to do this kind of things. But I'm just going to show you like a nice 1 minute promotional video to this. So this is a group of labs and companies coming together to study this, like attempting to form a foundation for studying human-to-robot transfer, right? So Stanford is actually part of it. So Shuran's lab was a like major collaborator for our efforts. And what we the Euro story is that we need a lot of data, so we collect a lot of, I'm going to talk about data set design and all that. So, but the number of hours is small, but it's growing, right? So this is not a fixed data set. We actually are continuing to pull together data from labs, from companies, to put together a common data source. So it's increasing as we're speaking. And we also did cross-institute study of a lot of these like basic hypotheses. Does aligning data actually matter if you have different robots, right? And it's really an ecosystem for studying this problem scientifically at scale. And it's made of 4 parts. One is data set. The other is platform tools. So we have different kind of ways to aggregate your data to allow you, anyone in this audience who have like maybe an iPhone, to collect the data. And we have a research study to really solidify some of the hypotheses we had throughout the journey of studying this problem. And we'll have a like consortium made of like academic labs and the industry researchers, industry startups to really come together, contributing data, insights, robots, and everything to study this problem. In data set design, we did it carefully to really to kind of divide it into 2 parts. One is what we call a flagship task, where we have unified task semantics, like folding shirts, like classic tasks like cup and saucer, which is actually invented by Shuran's lab. All of these tasks are standard semantics. We had many people across different labs, across companies, collect the exact same task on different environment, different objects, and different everything. So we have a common foundation for studying these tasks. And there's also a large pool of free-form data, like in the wild data that has a long-tail distribution behaviors collected by these companies, and then they contributed to the data sets. So that makes up the 2 parts of the data set. And like before, we really care about turning human data into robot-like data. So we actually added a lot of annotations, including these nice hand pose, head pose. And we also added dense language annotation on top. So it's very, very expensive to do this. And I'm really thankful for the company who actually did all of these annotations on these 1,400 hours of data. Okay, but moving to the future, all the data will have this kind of data density. And one of the most important design decisions for EgoVerse is that we don't want to just create one data set. We want it to continue to grow because we don't think 1,400-hour data is going to be enough to capture all of the possible human behaviors everywhere. Because a large pool of behavior that we haven't done is, I was talking to Mac today, is that like we want to study human-human interaction, right? Like a lot of these are still not captured in this data set, and we want everything to be kind of pulled together to this data source. So we actually had this thing hosted on Cloudflare. Its R1 instance was. Right now it's about like 10 terabytes of data, but it's still growing. It's 10 terabytes because we did a lot of compression, so that is manageable. And we also had a nice like SQL tables and data exploration web pages on top. So if you're interested, you can go explore egoverse.ai, the data browser there. And we know that not everyone can afford this kind of data collection effort at scale, so we decided to kind of make available, in addition to the Project Aria glasses, which is the default device we use in iPhone app that's able to allow you to capture this data. So it does, on the cloud server, it does data post-processing, labeling, and everything. So that you also collect data for yourself, for your own research, or contribute back to EgoVerse. Okay, so the third part of this is the study. So we cared a lot about like kind of a research debt. Like if you're familiar with this kind of technical debt for programming, you know, like there's a lot of assumptions we made, one-off assumptions we made in these papers. It has been pretty consistent, but we really want to show that it is true. And there are biases in our experiment setups. Different group have different robots, and different robot embodiment have different transfer. So we really decided that let's just have the same code base, same data set, different ways to collect teleoption data, same way to collect human data, and let's see what happens, right? Do we have a consistent finding across different robots? And what we found is that it's actually pretty consistent. So these are kind of tiny to see, but what we found is very similar to the conclusion of the EgoVerse, is that aligned data is very, very important to leverage diverse human data, the pre-trained diverse human data. And if you only train on diverse data, it's not going to give you much gain. So like diverse data plus aligned data is the key to enable transfer at this scale. And we're pretty sure about that across different robots embodiment. And one other thing we did was that we had discovered that operator, like despite I said that human have a unified embodiment, everyone is different. We have different body length. We have different habit of doing the same task. We have different ways to look at things. We have like different habit of like turning our head when I fold shirts and all that. So a lot of these diversity actually exists in human. And what we found is that if you, given the same data budget, if you train on more diverse human data, you actually improve the performance of generalizing to a new human embodiment. So there's some consistency to be learned, but you do need diversity in your human data as well to be able to enable transfer. So, and we also visualize this, that on the left side, this is a t-SNE plot of when you train the model with 4 different demonstrators versus 12 different demonstrators. So you can see that this red outlier, when you basically we had a holdout demonstrator and we projected back to the t-SNE map. And we saw that the outlier is no longer outlier when you have a lot more demonstrators. So it's a lot more mixed in when you have more demonstrators. Okay. So those are, I mean, there are many other things we did in this study. So if you're interested, go read the paper. It's quite fun. And also, you should contribute if you're interested. And the consortium is made up of a few different labs. So GT is led by my student, Ryan Simmer, left to students, and Stanford is led by Ziyi, UCSD is led by Roger, and ETH is led by a whole bunch of students with 2 PIs. So this is kind of our core labs, and this couldn't be possible without the support of these companies like Meta, Mecha, and Scale. So it's really like a marriage of like academic rigor, and we really care about studying problem, and they really care about trying to see what makes the data they collect useful so they can sell the data to other companies. So there's some synergistic relationship in this consortium. And we're continuing to expand. So when we release this data set, this thing, I got like, right now it's about 80 or so different entities and individuals who are interested in contributing. So we're continually enrolling new companies. And if you remember, I said there's more than 100 companies doing that. Yeah, some of them are interested in really understanding what makes their data useful. Okay. Okay, so that's EgoVerse, and then there's some other open problems I'm curious. I'm personally curious about. My lab's curious about. I'm going to briefly talk about it. I know we're mostly out of time. There's 5 minutes left. So what I'm interested in essentially is how to better model human. Essentially, what we are currently facing is that a lot of our model designs are based on assumption that we are learning from a teleoperative demonstration for tabletop task with a highly kind of damped system, basically. It's just like, if I summarize that, like very slow, moving at creeping speed, no viewpoint shifts, very short, like mid-horizon task, and we know how the demonstrator collected data, right? But when you're starting to talk about human data, things become a lot different. So what I'm interested in are two parts. How do we fully capture the experience of human, and how do we model it, especially the context of how human made decisions? And my first take is the first-person view is not sensory experience, is not the decision-making context used to actually decide what to do next. And one of the things that I'm very curious about is, can we measure force or tactile reliably from human? And right now, most of the development is on the visual side. These are nice things that the community, like the sort of the broader commercial sector have done, but the tactile capabilities are quite missing. Like tactile gloves are there, but they're not they're not good yet. There are like other technologies like EMGs to measure like muscle activations, all that as a proxy for force or how much force you exert, but they are not also very, very noisy. So there's a lot of immaturities in the hardware side for really sensorize the entire experience of how you how you perceive the world. And the second part is that the context for decision making is also more than just your instantaneous observation. You didn't make your decision about what you're going to do next by just looking at the picture you have in front of you, right? You have an enormous amount of knowledge. For example, this chef, right? This person cooked because, well, they have taken the class or they have been to a culinary school, right? And it's not because they just look at this image and they decide, oh, I'm gonna cook, I'm gonna turn on the heat, right? And the person, for example, turned to different workstations because they remembered that a minute ago they prepared their ingredients not on the table, and they had to kind of go back and kind of continue to do that kind of thing. So it's more than your instantaneous observation. And our models right now are terrible at modeling these kind of things. So there's a lot of work to be done to actually be able to what I call behavior clone a human. So if you really want to predict behavior of any person, what they're going to do next, there's a lot of research you need to do. And as a first step, our lab is doing a lot of different explorations. One of the things I'm most excited about is the spatial memory for mobile manipulation. So believe it or not, we have the technology to build a lot of these spatially consistent memories right now. So these are one of the ongoing works in our lab that we are building a dynamic, we'll call it dynamic scene graph of object being moved around as you're continuing demonstrating things. I've never seen these kind of things before. If you have worked on computer vision before, this is actually a new capability I've never seen before, that you can actually track objects and continuously integrate their point cloud on these objects to build better object over time. And this is all run in real time, right? So a lot of these foundation models, better devices, and better perception models are enabling these kind of technology. So I'm quite excited about this kind of research. So takeaways, human data is the largest data source of physical intelligence. Human-to-robot transfer is challenging, but showing promises. New capabilities emerge when model and data scale. And data is, in fact, scaling faster than our scientific understanding of these problems. And scaling science requires really a community effort. And with that, I'd like to thank you all. And these are the sponsors. Got a minute. Yeah.
So the multimodal that you mentioned at the end is very interesting, but as you mentioned, it's pretty expensive to collect. So I'm just wondering, from your experience with the diverse embodiments, would you expect to have a little bit of this expensive multimodal data make a big difference, so you wouldn't have to collect so much of it to have?
That's an excellent question. I think I expect yes. I think we could use these expensive sensorized human data as supervision to train models to label broader human experience. I think that should happen. But there are things that are just inherently not perceivable if you don't have sensors. For example, imagine that you reach in a bag and start to grab things. Without tactile, you won't be able to perceive it, right? You can't guess what you're doing. So these kind of things, not so much. But if you're talking about, let's say, am I in contact with this cup? If I look at from this, yes. I mean, I can perceive this from the egocentric view. So maybe I could use a model trained on tactile visual data to label this visual-only data, right? So that's definitely possible.
I am same thing as this multi-model. And you think about the neuroscience.
Yeah.
Neuroscience, and also the robotics learning reminds me of the baby, how the baby learn. And now your robotics right now is a baby, right? It's like very, how your machine learn versus how the baby learn.
Right.
I'm curious.
Yeah. Well, the neuroscience side of things is quite interesting because, I mean, if you're talking about like sort of planting sensors in people's brain, yes, this is the most direct form of human data. So maybe we can actually infer more intent from just like I don't know, the more better sensors. But in terms of the way robots learn versus human learns, I think right now it's very different. What we're trying to do is the way, like, it's sort of a like large language model analogy. We're not teaching large language model by teaching how to speak, like grammars and everything, right? We dump internet.zip into a model, right? What we're trying to do is to dump human.zip into a model and see what happens, right? Yeah.
You motivated your talk with LLM community and how data-driven learning has revolutionized that field. One thing that's been really important is data quality.
Yeah.
Yeah, and oftentimes when we talk about human data, it can be really noisy. What are your thoughts on like filtering out bad data, or like how do you do quality control, etc.?
Excellent question. I think that's the next stage of this. Like once we have more than, like I said, we're going to have more data than we know how to do it with it, right? So we could, the data filtering, understanding like how to explore the data, what data attribution, right? What data matters in pre-training sense that is the science of pre-training is just starting for these kind of models.
Mm-hmm.
Actually, a wonderful talk. Really inspiring and interesting work. I'm wondering if you can talk a little bit about what you observe after supervised fine-tuning. So what I understood, pardon me if I'm wrong, in the middle projects where you were pre-training with large data and then testing on specific tasks, you were still pre-training and then mid-train and then supervised fine-tuning.
Yeah.
Do you obtain any degree of generalization after supervised fine-tuning?
That's a great question. Yeah, we didn't really stress test this, but we, in the paper, but really did a lot of testing. I can't talk too much about this. Like, this is part of the NVIDIA project. That I can tell you that it does. It does have a lot of transfer from human knowledge, not in the form of mostly. Some in the form of spatial generalization, object generalization, but what's most surprising is that language following became much better. I don't know why. Like, we don't have a good hypothesis of why language following became much better when you pre-train on human data. But yeah, compared with other frontier models, like human trained data is actually most effective. Like, we can actually do, like, for example, negative steering. Like, we can actually say, don't do this, and actually like try to avoid that object when it's trying to do it. Yeah.
Follow up, your human data is also language labeled, right?
Yes, yeah. That's right. Yeah, that was the reason. Yeah.
For other applications, there's been a push towards synthetic data to amplify the current existing data. Have you also seen that with vision models for robotics, or are the general models not there yet?
Sorry, can you rephrase your question?
Oh, so like synthetic data is really important for other applications, like for depth, for instance, because it's more reliable. But then, have you seen people using like generative AI images or videos, or just simulation?
Great question. So the thing is that the synthetic data is useful because you want something scalable, controllable, and maybe contain some characteristics that you want from the data that you can manually inject, right? But for human data, right now, we can actually, like, the way that we, for example, tell our vendors to collect data is we can have the high degree of freedom of control over what behaviors they have. So for now, I think it's okay to only rely on like realistic real world data, but in the future, definitely synthetic data will be very useful. And the one place that where it's very, very useful is the last inch of between your hand and the object, because human hands are still very different from robot hands, right? And the way that we interact with the object will be subtly but importantly different from how robots should interact with the object. And this last inch or last Newton difference is going to be like like basically you want to answer the question, if I were a different person or different robot, how I should have done this in order to cause the same effect of this, what I've demonstrated, right? So that kind of counterfactual data doesn't exist in the real world. You have to synthesize it.
With language models, the big breakthroughs happened first in languages in which a lot of text was already available. But then there are also translation models to convert that to other languages. So for parts of the world where neither Arya nor iPhone would be very common, do you think that the different kinds of scenes or different ways of doing things could still get some translation benefit from training on these kinds of data sets?
Are you talking about like cross device difference or across behavior?
Very different kinds of objects maybe, or different human preferences of how tasks are done.
Right. So like how, like basically, do we need like everybody doing the same task the same way, or like diversity, behavior and diversity, right? Yeah, that's a really good question. I think there's this, I would say there's a paradigm shift to how right now as to like how do we design these models, right? Again, like I said, the VLAs or a lot of these behavior cloning models are designed to fit uni strategy data. And right now, you can't really constrain human behavior. If you want to learn from natural links to human behavior, you can't constrain them. Like that's our goal, right? So in order to solve this problem, we really need a new type of model to be able to fit this kind of data. And diversity, I would say, is the thing. It's a problem, not a solution. Really, we want to solve that in order to leverage more data. Yeah.
Another question: what do you think is the future of teleoperation given all this development? And how do you think robotic companies will evolve their investment in teleop given how obviously expensive?
Are you a VC? Sorry, I'm just kidding. Because I will give it a different answer. So, yeah, I think my personal goal is to get rid of teleoperation, because this is just, like I said in the beginning, it's a lossy pipe. Like, I really want my robots to be human-like. For example, if I throw this water bottle at you, you would either catch it or you flinch. I want my robot to be able to do the same thing. You would not be able to teleoperate that to demonstrate this repeatedly. This is all natural human behaviors, right? I want that to happen. This is my personal goal. Yeah.
Questions?
Oh, sure.
What's your opinion on hand embodiment and how much it should match human hands?
Oh, great question. Yeah, so I would say, yeah, like what I said, like the last inch gap, right? Like if your hands is very human, like if your robot hands is very, like if there's no difference between your robot hands and human hand in terms of kinematics and dynamics capability, you can move really fast, you can move flexibly. You don't need to bridge the gap, right? It should just work. But we're not there yet. So the less human-like your robot hands or infactor or the whole body is, a bigger a gap you have to bridge, and the actual transfer that happens will be different. For example, like let's say if I have a higher degree of freedom hands than human hands, then maybe the thing we want to retarget is not the actual kinematic configuration, but contact, right? I want the contact to happen at this point in time in this space, like here, right? And if I have ways to exert force similar to how humans do and can measure force, then this is what we should retarget. And then the rest of the configuration doesn't really matter, right? You define a task space, the rest you hand over to like a IK or inverse dynamics or learn solver, right? Yeah. So basically, the bigger the gap, the more work you have to do, like to enable transfer. Yeah. Wow, it's a lot of great questions. Thank you.